Let's move on to rethinking Atrous convolutions. Why do you want to rethink it? Because there are two challenges when you are trying to do deep learning and actually deep convolution on neural network for semantic segmentation. One is you are going to end up with reduced resolution for two reasons. One, you are doing transfer learning from a classification task. By nature, you are shrinking the resolution from one layer to the next one. The other one is you have to reduce the feature resolution because you need to know what is in that object. You need to look globally, summarize your entire image in a bunch of smaller vectors. And then the other challenge is you can have objects at multiple scales. Some objects are small, some objects are big. And we saw a couple of solutions for this. One solution, we saw a modification of this with bounding boxes. You don't need bounding boxes. You can actually scale your input image. Input multiple images with different resolutions in your neural network, and then merge them at the end. Let them vote. What is the downside with this? You have to take your image and push it through multiple layers of deep neural networks. And then you're doubling the cost, tripling the cost, and more, depending on how many input resolutions you have. Equivalently, somebody might say, why are you inputting multiple images? Your convolution is already doing that for you. This convolution here is looking at the smaller scales compared to this one, which is looking at larger scales or larger portions of your image. And this last one is perhaps looking at your entire image. Just have shortcut connections. The last one is looking at the what of the picture. These lower ones, lower layers, are looking at the where of your objects. They are less informative in terms of what is in your object, but they are good at detecting boundaries. And just combine them, have shortcut connections. And this type of idea we cite in UNet. Another one is if you want to end up with a higher resolution feature map after a couple of layers, rather than using plain vanilla convolutions, use convolutions with holes or Atrous convolutions, dilated convolutions. And you're going to be able to preserve or at least end up with a higher resolution feature map in the end. Another solution, this is especially useful when you want to look at your images at multiple scales, is rather than having Atrous convolutions per each layer, put them next to each other. Rather than having them sequentially, have them in parallel, and then concatenate them in the end. And this is able to look at your image at multiple scales. A quick recap of the mathematical formula for Atrous convolution. You take your weights, which you can do transfer learning on them. These could be pre-trained, and then you can then fine-tune. And then you apply those weights every other pixel or every R pixels apart, like what you're doing here. Your rate could be 1, which is going to end up being the same as a regular convolution. Your rate could be 6 pixels apart, 24. And this is how you're looking at your bigger regions of your image. And let's take a look at how the depth is going to work. If you start with an image, and then let's say you have a convolution with some pooling, and they have a stride of 4, then every single pixel in the output in this particular feature map and the next one, in this layer, they're going to be 1 pixel apart, but in the corresponding pixels of your image, they're going to be 4 pixels apart. After another block, they're going to end up being 8 pixels apart. Each pixel here, each pair of pixels here that are next to each other are going to be 8 pixels apart in the next layer. And then you keep doing that. You keep shrinking your resolution and then increasing your output stride. What if you do this for a couple of iterations? That's fine. And then replace these convolutions, same parameters. Just apply them every other pixel or every 4 pixels, every 8 pixels. Then you're going to be able to preserve the resolution from one layer to the next one. All of these are going to have the same resolution and the same stride. Let's see what's going to happen. If your output stride is 8, you're going to have the highest mean intersection over union. If you keep shrinking up until you're here, you're in the panel A of your figure, then mean intersection over union is going to drop drastically. Another thing is depth matters. Whenever you're deeper, your neural networks are doing better. in terms of mean intersection over union. And then you can say, I want to preserve the resolution up until block 4, and then cut my neural network there, and then go back to the resolution of my original image, and then do per pixel prediction. Or you can cut at block 5 while preserving the resolution. It turns out that you need to cut later in your neural network. It means that depth matters. Actually knowing what is in your image matters. Not only that, each one of these blocks are a combination of convolutional layers. We can play around with their rate, with their Atrous rate, and then you can test them. The first one is just a simple convolution all the way. The next one is a simple convolution followed by an Atrous convolution with rate 2, and then a convolution with rate 1. And then you can see that this one is doing the best. So these are all of the experiments that you're doing to design your neural network. The next idea that we saw, so now you're combining these two ideas together, was putting them next to each other. We can do that. Put your Atrous convolutions in your last layer next to each other. The novelty of this work is borrowing ideas from what we just saw with pyramid spatial pooling. You can pool your entire feature map into a single vector. This is going to give you information about what is in your image, concatenate all of them, push them through a one-by-one convolution, and then do the rest of your neural network. And this is the architecture that you're going to use. You're going to use multi-grid with a grid that goes a simple convolution, a convolution with a stride with rate 2, another Atrous convolution with rate 4. This is a tick here. You're going to use Atrous spatial pooling, which is this operation here. And at the same time, you're going to pool your entire image into a single vector, put it here. And then you can look at the predictions of your model. And it's doing the best. It's the third version of DeepLabv. And JFD, if you remember, it's a data set from Google. It's much bigger than ImageNet for image classification. You can do your transfer learning on that, pre-train on that data set, and then fine-tune. And then there is this idea of what if your neural network is going to be able to classify or do segmentation on simple images, and it's going to have a hard time focusing on harder images towards the end of the training. Towards the end of your training, you can actually show your neural network more and more harder examples. And this is something that is called curriculum learning or hard example mining. We're going to see that later on. Not today, but down the road. Any questions about this? I think this one gave us a good overview of the type of methods that we have covered so far. One of them was input images at multiple scales. That's one idea. Another one is encoder-decoder type of architectures, like UNet, using Atrous convolutions and going deeper. This is multi-context and DeepLabv. The other one was spatial pyramid pooling type of ideas, and then pulling the global image and putting it as one of your vectors. I think it's a good time for me to stop. For those of you who have questions, I'll be around.